Hello, algebra students. I am filming this video while sick, so I do apologize for my voice, but I wanted to make sure you got today's lesson, which is going to be on interpreting and using function notation. The objective for this lesson is we're going to use function notation to talk about functions. There's two things we're really going to focus in on in this lesson, and that's with function notation when your input and output might lead you to think a little bit more about what numbers they're actually talking about, and how function notation can help us describe graphs of functions. So for our warm-up, there's 5 questions here about the numbers 1 million and 1 billion. I'm going to ask you to go ahead, pause this video to think about these 5 questions, and then come back when you're ready to discuss. All right. So as I said, each of these questions are about the numbers millions and billions, specifically what those numbers look like when you write out all of the numbers instead of just the word million and billion. So for that first one, the number 1 million, if we're saying 1 million, million means there's going to be 6 zeros after that one. So we've got 1 million and then 1, 2, 3, 4, 5, 6 zeros. And lots of times, especially when the numbers are that big, we use those commas to separate it out. So 100.2 million is going to be similar to this. 100 million would mean I've got the number 100 and then 1, 2, 3, 4, 5, 6 zeros after the number 100. But it wasn't 100 million, it was 100.2 million. So that means where that comma is, that's kind of like my decimal. And so that first zero, instead of being a zero there, would be the number 2. So we get 100.2 million would look like 100,200,000. That's going to be similar for down here when we start talking about billions. 10.5 billion. Well, first 1 billion. 1 billion is going to be the number 1, followed by not 6, but 9 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So that's 1 billion. Knowing that's going to be important for 10.5 billion. 10.5 billion is going to be 10. But instead of 9 zeros, that first zero right there is going to be that 5 from the 0.5. So we get, and then 1, 2, 3, 4, 5, 6, this number here. That's our 10.5 billion, or 10 billion 500 million. Knowing these first 3 help us when we start trying to change things from billions to millions, or knowing how many millions are in a number. So for 2 billion, first I'm going to write out what 2 billion looks like, and that's going to help me figure out how many millions are in it. 2 billion would be my 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros after that. So this is 2 billion. My millions, remember, have 6 zeros after it. So millions start right here. So 2 billion would be the same thing as 2,000 million. My eyes messed up there. So 2,000 million is the same thing as 2 billion. And then there's one last one. How many millions are in this number here? If I said this out loud, that's 54,200,000. So again, those millions start where I put that purple line right there. So after that second comma, if I'm working from the back. So knowing that helps me with 54.2 million. That's how many millions are in that number there. This might seem like a little bit of a random warm-up, like we've never talked about millions or billions before, but this idea of being able to change millions into billions and understand what all these numbers look like are going to be helpful for our first math problem below, which is going to continue talking about millions and billions. So with that, we'll go ahead and transition to the next part. The first math problem we're going to spend a lot of time looking at is all about smartphones. So coming down here, we've got the function P gives the number of people in millions who own a smartphone T years after the year 2000. Now, before we even jump into any of the math problems, as soon as I see we're talking about functions, a good thing just to do, even if a question doesn't ask you to do it, is ask yourself, if it's a function, there's got to be an input and an output. What is the input and what is the output? Go ahead and think through that question now. For this function P, what would our input be and what would the output be? I'm going to go ahead and label the sentence. Our input would be the years. My input is this part here that I'm going to mark in purple. And then our output would be the number of people who own a smartphone. So that part in green there is going to be our output. The input is the years because it's kind of like me saying, if I tell you how many years after 2000, you would be able to tell me how many people own a smartphone there. Sorry. Knowing the input and the output is going to be helpful when we start seeing these questions below that are in function notation. One of the things we had talked about yesterday with function notation is when you're looking at function notation, you've got the name of the function in front of those parentheses. Inside the parentheses is always going to be your input. And then if it's an equation, what comes after that equals part is going to be your output. So now we know, using these labels we came up with for input and output, when we come down to number 1, we know what those two numbers are going to be describing. The number inside the parentheses is going to describe our input, which is this here. And what comes after that equal sign is going to be our output, which is right here. Now, notice the input and the output are really specific with the measurement. It didn't just say the number of people who own the smartphone. The output said the number of people in millions who own a smartphone. And similarly, the input wasn't just the year, it was the number of years after the year 2000. That's going to be really important again when we start looking at function notation, and like in number 1, we're trying to figure out what these two equations mean. So I'm going to have you go ahead and just start with A, keeping in mind everything we've said so far about this problem. Go ahead and pause the video and see if you can figure out what that equation there is trying to say. All right. So connecting it to some of the things we've already mentioned, what's in my parentheses, the 17, is describing our input. The input was this part in purple, but it doesn't mean in year 17. First of all, that sounds crazy. It means 17 years after the year 2000. So 17 years after the year 2000 would be the year 2017. So somewhere in that description of what that equation's telling you, you want to mention the year 2017. If you said 17 years after the year 2000, you're not wrong, but we can go ahead and make that clear by just saying in 2017. We could actually do that math, right? Similarly, this other number here, that one after the equal sign, was our output. Remember, our output's talking about the number of people who have a smartphone. But that number, 2,320, it's not 2,320 people who have a smartphone, because our output wasn't just the number of people. It's the number of people in millions. So that means 2,320 million people own a smartphone. So this is where that warm-up comes in handy, right? If 2,320 million people own a smartphone, that must mean in 2017, 2,320 million is going to look like this. I know when I see that word million, I'm adding those 6 zeros, right? So we get 2,320 million is going to look like this number, which is actually 2,320,000,000 people. That's a ton of people. So in 2017, 2,320,000,000 people own a smartphone. Now, this is a great chance to talk about why are we doing this? Because it is a little more complicated, right? I'm not going to lie to you. We're looking at this number here and we have to convert it into millions. But the benefit of doing it is obvious right here in this statement. I didn't have to write out that crazy long number. By changing what the measurement is, it helps save us time and space by making these numbers a little easier to work with. So now that you've got an example to work off of, go ahead and pause the video and try part B. Similarly, you're going to come up with a sentence like this that this function notation right here represents. Go ahead, try that now. All right. For the second one here, our input is the number -10. We've got to think about what a negative number here would mean. The input is the years after the year 2000. So if my input is negative, it means we're talking about years before 2000. 10 years before the year 2000, what year would that be? 10 years before the year 2000. That's going to be the year 1990. So this function notation here is telling me about the year 1990. So in the year 1990, we've got a 0 here. That 0, remember, is your output, which is the number of people who own a smartphone. So that's telling me 0 million people own a smartphone. Well, 0 million is just 0. So we could make it even better and just say in 1990, 0 people own a smartphone. That right there would be the best answer. Similarly, that's our best answer there. Now, why is that? Why is my output the number 0? Well, if you happen to be alive in 1990, the reason the output's 0 is because smartphones didn't exist yet. So this is just letting me know we're talking about years before 2000, and by the year 1990, if you're working backwards in time, there is no one who owns a smartphone yet because they don't exist. That gives us an idea too of why the input, instead of just being years, is specifically the years after 2000, because that's really where we see the amount of people who own a smartphone increasing and being sizable numbers. Now, this first part was us taking the function notation and describing it with a sentence. The second part's going to be the opposite, similar to what we did yesterday, except now remember, you really have to think about what number you're going to use for your input and output. We're seeing it's not just as easy as taking the number 2010, right? We're going to have to think about these measurements that were being used to describe your input and output. I'm going to have you go ahead, pause the video now, and go ahead and try number 2. See if you can come up with function notation to represent those. All right. So for this first one, it's talking about the year 2010. I know my function notation is going to start with the name of the function, which is p, and then inside the parentheses is our input, which, using what we had marked from earlier, the input, remember, is the years. But we can't put the year 2010 there. We can't have the number 2010 be our input, because that would mean 2010 years after the year 2000. That would be the year 4010. Instead, I need to do some quick mental math. 2010 is going to be 10 years after the year 2000. So our input should be the number 10. Similarly, my output, remember, is the number of people in millions. So I have to think about this number here, 2,096,600,000 equals how many millions? You did something similar to that up here. Up here in the warm-up, specifically this last question where I gave you that number there, the 54,200,000, and I asked you how many millions that was. This right here is going to be similar, where that second comma right here is where my number for million starts. So we're going to say 296.6 million. Our output in this one right here is going to be P of 10 equals 296.6 because that output represents how many millions. Oh, I'm sorry, guys. The second part here is going to be real similar. Our input for 2015, that's 15 years after the year 2000. And then for our output, we have to think about what 1.86 billion looks like in millions. 1.86 billion would be 1,086,000,000. So that would be this number here. So if I wanted to change that into millions, again, I'm really trying to focus on what comes in front of those 6 zeros. And so that would be the number 1,860 billion. So my output right here would be 1,860. I know changing millions and billions can be complicated, especially if you've never seen it before. It's just been a really long time. I do want to let you know, though, I think this is like the most complicated it gets. But you've done stuff like this before. Like when we talk about 60 seconds, how many minutes is that? And having to think about it as 1 minute. Or when we talk about similarly like hours, if you have 0.5 hours, knowing that's 30 minutes. So you've done some of these conversions before. This is really just illustrating how it's important regarding function notation. We're going to get a chance to do some of these conversions at the very end of this lesson. There is one last question. We've got May is curious about the value of t in the function notation equation here. P of t equals 1,000. What would the value of t tell May about the situation? Looking at this here, I think, again, it's helpful to have this part right here in blue in mind as I'm trying to figure out that. Go ahead, though, and see if you can figure out number 3 on your own. What would T tell her about the situation? Well, T, it was in the space where our input's going to be. So it's going to be telling her a year. It's going to tell her however many years after the year 2000 that something happens. That 1,000 right there as our output is describing how many people have a smartphone. So T would tell her how many years after the year 2000 that 1,000 million people owned a smartphone. And the only thing I would change about what we've got written here is what 1,000 million people look like. I know the word million's telling me 6 zeros are going to come. So, oops, not at the end of my sentence, though. So I get 1, 2, 3, 4, 5, 6. 1,000 million is the same thing as 1 billion. So T is going to tell her what year 1 billion people own a smartphone and what year that milestone happens. These last 2 questions here are just 2 questions to think through in the situation. We've kind of touched on them a little bit as we've worked through these. Go ahead and see if you want to think through these 2 questions and what you come up with. It has to do with why we're making these inputs and outputs more difficult. I think the answer is really kind of the same for both of them. By focusing on these measurements we're using and using the measurement millions of people instead of just number of people and years after 2000 instead of just what year it is, it helps because it makes the numbers we're working with a lot smaller. Like if I look at some of these function notations we had written before, notice both those numbers in our equation are smaller. I'm talking about this huge number, but I'm only writing down 296.6. And I'm talking about the year 2010, which looks small in comparison to this number over here, but it's still a really big number. But I just have to use the input of the number 10 to represent my input. And we're seeing that across the board with all of these. I'm not going to have us graph this situation, but if we wanted to graph this, this is going to be super helpful because now my graph doesn't have to get up to 1 billion on our y-axis. Could you imagine trying to scale your graph so that it goes up that high? Instead, my graph just has to go up to the number 1,000, which is much easier to handle. So it does take a little more thinking about the input and the output in terms of millions of people in years after 2000, but it helps make these numbers smaller that we're working with. This first part here was really a chance for us to talk through inputs and outputs when they're not as straightforward. The second part of this is looking at function notation that we've been practicing in this first part and how it can relate to the graphs we introduced in the first 2 lessons. And so to help us talk through that, we've got this other math problem about boiling water. So in this scenario, the function W gives the temperature in degrees Fahrenheit of a pot of water on a stove T minutes after the stove turned on. Now I'm going to take my advice from earlier in this lesson. As soon as I see we're talking about a function, let's pause. Let's pause right here and think about what is the input and what is the output in the function. I promise giving yourself that extra step is really going to help you when you start jumping into the function notation. So go ahead and do that. Pause this video real quick and see if you can figure out what the input and the output are going to be. Oh, goodness. I'm sorry. But you're back now. You're back now with some answers. Our output here is going to be the temperature in degrees Fahrenheit. So that first part here. And then our input is going to be the T minutes after the stove turns on. So just like the number of minutes the stove has been on. Knowing that is going to help us when we jump down into this next part and we see all this function notation. So for number 1, it's this task of you working with a partner to explain the meaning of each statement in this situation. And that just gives good advice for when you're working with a partner, right? When it's your partner's turn, listen carefully to their interpretation. If you disagree, discuss your thinking and work to reach an agreement. Basically, you're working with a partner to see if you can figure out what these 6 statements here are saying. So you're coming up with like a phrase or a sentence to describe each of these. We were doing that up here with these first 2 questions. I think the biggest difference is up here, we were only working with equations. And look here, we've got some inequalities mixed in too. Go ahead and try to come up with these 6 statements and what they're describing. Checking back in with these first 3 written out for you. So that 0, the 5, the 2, the 10, all those numbers in parentheses represent our input, which we said earlier is the minutes, specifically how many minutes after the stove was turned on. For this first one, you can talk about it as 0 minutes after the stove turns on, but we've talked about that 0 really representing like a starting point. So I decided to phrase mine as the temperature of the water starts at 72 degrees. Or you could say the temperature of the water is 72 degrees before the stove turns on. Both of those work out. These other ones, that inequality is telling me the temperature of the water after 5 minutes is going to be greater or higher than the temperature of the pot of water after 2 minutes. And then that third one there, the temperature of the pot of water 10 minutes after the stove is turned on is 212 degrees Fahrenheit. If you were struggling a little bit for these, use these first 3 as examples to help you finish up those last 3. If you're feeling good and you feel like you've got all 6, go ahead and just keep watching this video. And I've got these last 3 statements here for you. Statement D is telling us that water temperature is going to be the same at 10 minutes and at 12 minutes. Notice this equation here doesn't tell me what that temperature is. I know though from part C that at 10 minutes the temperature was 212. So I could use that to help me figure out this is telling me the temperature is the same at minute 10 and minute 12, which means at minute 12 it also must be 212 degrees. Part E is similar. It reminds me of the statement in B. the temperature of the water after 15 minutes is going to be higher than after 30 minutes. And then F is the opposite because now we've got a less than sign. So it's telling me the temperature is lower at 0 minutes, or I use the word colder. And instead of saying 0 minutes again, I was talking about like that beginning or that starting point. So I came up with the sentence, the pot of water is colder at the beginning than 30 minutes after the stove is turned on. Again, function notation isn't something we learn in a day. So as I promised in that last lesson, we're going to keep practicing this again and again throughout the unit. But hopefully you're feeling yourself get a little more confident each time you see one of these. For this last part here, we're going to take all 6 of these statements we just analyzed and use them to help us create a graph. Now, looking at this, notice we don't have all the information. We just have 6 of these equations or inequalities to help us. So some of this is going to be a guess. It's going to be an estimate. But we can use some of these specifics, like this first one, for example, to help us know where specific points on our graph should be. And then kind of like what you did in that math question about the dog tied to a post, we can kind of fill in the rest of that graph um, using some reason. So if you're feeling confident, go ahead, pause this video and see what you can come up with for this graph. All right. When I go to start my graph, I'm going to start with that starting point, which I do have a concrete number. I know at 0 minutes, when we're starting off, the temperature is 72 degrees. Looking at my y-axis here, I see 50 and 100. So I know that line in between them is going to be halfway, which is 75. So I'm going to have my point be just below that. That's as best as I can estimate. We know from this next statement that the temperature is going up. That should make sense. If you've ever put a pot of water on a stove, right? It's heating it, so the temperature goes up. So I know at 2 minutes, that line right there is halfway between 0 and 5, which is going to be like a 2.5. But I know at 2 minutes, the temperature is lower, and at 5 minutes, the temperature is higher. So I can just have my line going up here. I'm going to hold off doing that until I have another concrete point, which I do here with statement C. I know at 10 minutes, the temperature is 212. So I'm going to go to 10 minutes, and then I want to go up to 212 degrees. This line here is 200. This next line would be 225. So that's really like almost in between 200 to 225. And then I'm just going to guess the temperature is going up like pretty constant. So I'm going to do something like this. I can go back and check statement B. I could see at 2 minutes and at 5 minutes, look at that. The temperature at 5 minutes is higher than the temperature at 2 minutes. At 5 minutes, according to my graph, I'm guessing it's going to be around like maybe 130 degrees. And at 2 minutes, it looks like it's around 100 degrees. So that statement B checks out. Coming down to statement D, I'm just going through them in order of time, right? So next comes 12 minutes. We said the temperature at 10 minutes and 12 minutes is going to be the same. Well, at 10 minutes, the temperature was 212. So that means at 12 minutes, the temperature should be about the same. So that means my line is going to start going flat. That's just, I'm trying to make it flat because that temperature is remaining constant. Looking at part E, it's saying the temperature is higher 15 minutes than at 30 minutes. So at 15 minutes right here, that should be higher up than at 30 minutes. So based on that, if 15 minutes is going to be higher, it looks like my line might be going down like that. 15 minutes right here, 30 minutes I've got down here right now. What do you think is happening if that temperature is going down? Well, my guess is the stove was turned off maybe or turned to a lower temperature. When I get to this last one, we're saying the water was colder at the beginning than at 30 minutes. If I'm looking at my graph right now, I made them the same temperature, so I'm going to have to do some adjusting. That line I had going down, it still should go down, but that final temperature, 30 minutes, needs to be higher up. So maybe I have it go like this. I don't have any actual temperature, like I wasn't given the degrees to work off of, but I do know that 30 minutes, this point here should be higher than our starting point, than that y-intercept. Your graph might look different, and that's completely valid because remember, we don't have all the information here. But it should have each of these 6 statements be true on your graph. This was the final math activity for this lesson. There is one final thing for you to look at, and that's a cool down. So this is going to be like a Thursday check-in for this. The cool down is longer. It's got 6 questions, which I know is a lot, but it's longer because it's got review questions on all 3 of the lessons we've covered so far. So at this point in time, I encourage you to go ahead, pause the video, and try to complete the cool down, and then come back to get those answers. All right, and you're coming back for some answers now. For this first part, notice I put that question in about the input and output just because being able to identify those is so important. You can get them from this description here, but there's also like an extra thing you could have used. There's the graph at the bottom of this that could also help you because we've learned your input is always going to be on your x-axis and your output is always going to be on your y-axis. So using that information or just information from the story here, you can come to the conclusion. The input is going to be how many hours after opening it is. The output's going to be the number of visitors the museum has. From that's going to be really helpful when we try to find this function language. Remember, one of the things we've learned in these first 3 lessons is that phrase, what is a function of what? And what we've learned is you can think of is a function of as that phrase, it depends on. And so using that, we could conclude the number of visitors is going to depend on how many hours the museum's been open. So that would be option A. Or some of us like to just remember that the output's always going to come first. We've got your output is a function of the input. So it's up to you how you want to do it. I really like to rely on that phrase, depends on, to help me figure it out, but that's just me. If you like to just remember that the output is going to come in front of that phrase, you can do that too. When it comes to number 3 and explaining what this right here means, it's similar to that question we had done with the smartphones and the millions and billions. We really have to think about what the input and the output represent. The output is a little more straightforward. That 28 is our output, and it's telling me there are 28 visitors. Let me switch over to text. So I could say there are 28 visitors. That 1.5, though, is a little more difficult. That's not talking about like 1 p.m. or 1, I don't know what the 5 would be, 1:05 p.m. Remember, your input is the hours after opening. So this means 1.5 hours after the museum opens. Since we know the museum opens at 9 a.m., we can do that calculation. What's 1.5 hours after 9 a.m.? Well, 1 hour after would be 10 a.m., and 1.5 would be, oh, I'm sorry, would be 10:30. That 0.5 means half an hour or 30 minutes. So 1.5 hours after 9 a.m. is 10:30 a.m. So we could say there are 28 visitors at 10:30 a.m. there. That's similar to what we're going to be doing down here, except now we're flipping it around again, where we're taking the statement and we're coming up with function notation. Just like we were saying before, whatever's in your parentheses is going to be the input, which we've set up here is that time or the hours. So I know that 1 p.m. is my input, and that's what I have in parentheses. Now that 1 right there might have been really tempting, but again, your input is the hours after opening. By 1 p.m., how many hours after opening is that? How many hours has the museum been open at 1 p.m.? Well, starting from 9 a.m., I'm going to count up. So 10 a.m., 11 a.m., 12 a.m., 1 p.m. That's 4 hours after opening. So that's where that 4 is coming from. I'm going to pick C because we said, remember, our input is what goes in parentheses. So my input 4 hours after opening goes there. And my output, the number of visitors, is going to be after that equal sign. Again, I'm using that idea of with function notation, our input goes here and our output goes here. If you had picked D, D is saying 257 hours after opening, there are 4 visitors. So even though it's the right numbers, it means something different if you flip around where those numbers go. There's 2 more left. 5 is similar to 4, except now it's not a multiple choice. In 5, we're trying to write this statement using function notation. The statement is, at the time of closing, there were no visitors in the museum. I know function notation is going to start with the name of the function. And then in parentheses is going to be our input. Our input is time, and they're talking about the time of closing. Do I know what time closing is? Why, yes. Yes, I do. It's up here. It closes at 5 p.m. So my input, hours after opening, how many hours have they been open by 5 p.m.? Well, again, I'm going to start at 9 and I'm going to count up. So 10 a.m. would be 1 hour. 11 a.m. would be 2 hours. 12, 1, 2, 3, 4, 5. I'm at 8 now. That's 8 hours after opening. So my input is going to be 8. That's saying 8 hours after opening, there are no visitors. My output is the number of visitors. So I've got to convert that to a number. No visitors means 0 visitors. So I want that output to be the number 0. At this point, we've got a couple different things we know now. We know at 10:30 a.m. there was 28 visitors. I know at 1 p.m. there were 257 visitors. And I know when they close 8 hours after the museum opens, they have no one, which makes sense because they're closed. Using those 3 pieces of information, we're going to come up with a graph. I'm gonna guess that at opening they're starting at 0. They never told us that, so you can, I guess in theory, start anywhere, but I think 0 is what makes the most sense, right? There's no one there yet when they open, unless they had a line. But for me personally, I'm going to start my graph at 0. I know 1.5 hours after they've opened, so that's right here. They should have 28 visitors. So that's not that much. This line right here is 40. So 28 visitors is going to be about 3/4 of the way up. So I'm going to put my point right there. It looks like I marked a point there, but I was just trying to show where 1.5 is. So I got that. And then the next thing I know at 4 hours after they've opened, or at 1 p.m., they have 257. So 4 hours after they open, they have 257 visitors. That's going to be around like right here. And then by the time they close, they're down to 0. So 8 hours after they've opened, they are down to 0 now. So those are the 4 points I know. Well, I guess 3 points I know for sure, and I'm guessing they're starting with 0 visitors. So the rest of this, I'm just going to connect those points with a line. Of course, your line might look different, like maybe it goes higher than that. But we know our line should connect between those points. Your graph, like I said, might look a little different, but you want to make sure you've got those points there in purple on your graph. Thank you so much for watching. Thank you for your patience while I'm out sick, and I am excited to see you all soon. Bye.